Hello everyone. In our previous discussions of this 2D elasticity chapter, we had been time and again referring to this all important biharmonic equation. So we had this del 4 phi equal to 0, and uh, in the rectangular Cartesian coordinate system, the expansion of this was like this: del 4 phi del x4 plus twice del 4 phi del x square del y square plus del 4 phi del y4 is equal to 0. Now, when we wish to go over to the solution of such problems where the rectangular Cartesian coordinate system is not very convenient, rather it is the polar coordinate system, that is the r theta coordinate system, which is a more natural choice for the solution of the problem, then what do we do? Well, to answer that question, we could proceed by two routes. First, we could reframe our entire theory starting from the kinematics chapter through the stress chapter, material behavior, as well as all the discussions involved in 2D elasticity, that is to say the plane stress discussions and the plane strain discussions in the r theta coordinate system, and then arrive at the counterpart of this biharmonic equation in the r theta coordinate system. That is the first route. Or we could take a shorter route and arrive at the polar version of this biharmonic equation directly from this rectangular Cartesian coordinate version. So all that we have to do is to recognize the very well known from our high school days, the relations that x is equal to r cos theta and y is equal to r sin theta. If we have these, then we all know that we have x square plus y square is equal to r square, and y by x is equal to tan theta. From these two relations, what we can do is convert these derivatives del x del y in terms of del r del theta. It's not going to be very straightforward, but we can find out the conversions from this xy system to the r theta system, and that is exactly what we'll do. And for this development, what we'll do is we'll follow the route that is presented in the classic book on elasticity by Timoshenko and Goodyear. Okay, so as a first step, you please note that we can find out del r del x from this relation. So what we can do is we differentiate this relation with respect to x. So what I'm going to write here is basically the right hand side first and then the left hand side. So you understand that when I differentiate this right hand side with respect to x, this is going to be twice r del x, and on the left hand side I'm just going to get this as twice of x, and this is easily simplified as x by r, and since x is equal to r cos theta, we have this del r del x as cos theta. Next, in a very similar way, we can obtain the del r del y simply by differentiating this relationship with respect to y. So we have twice r del y is equal to twice y, and that gives us del r del y is equal to y by r, and y by r from this relation here is nothing but sine theta. All right, next in order to find the corresponding derivatives for the theta, that is to say, instead of del r del x, if we want to find out del theta del x, we have to consider this relationship. And for that, we'll again differentiate this relationship with respect to x first and then with respect to y. So here, if we differentiate this with respect to x, what we'll obtain is minus y by x square is equal to sec square theta del theta del x. All right, and this will give us del theta del x is equal to minus y by x square cos square theta. However, y is equal to r sine theta, we replace that, and x is equal to r cos theta. So this is r square cos square theta, and we also have a cos square theta here. So this cos square theta cancels with this cos square theta, and ultimately what we have is minus sine theta by r. In a similar fashion, let us do the differentiation of this relationship with respect to y, and what we'll obtain then is 1 by x is equal to sec square theta del y. So that del theta del y is cos square theta by x, and just replacing x by r cos theta, what we'll obtain is cos theta by r. So we have this relationship here. This is our del r del x, just the cos theta. We have the del r del y, which is just the sine theta. This is our del theta del x, and this is our del theta del y. All right, now why did we do all this? Why did you find all these expressions? The reason is simple, that given any function f of r and theta, can we find out the derivatives with respect to x and y? And let's see how we can do that using the chain rule in the next line, in the next page. So what we want to arrive at is del f del x, but written in terms of the derivatives with respect to r and theta. So using the chain rule, what we have is del f del r times del r del x plus del f del theta del x. So here we are proceeding with the understanding that this f is a function of r and theta both. In a similar fashion, for del f del y, we have del f del r del y plus del f del theta del y. So you see, in the previous page we had already obtained the expressions for del r del x, del r del y, del theta del x, and del theta del y. We can directly use those expressions here, and given a particular form for this f, for this function f of r and theta, we can easily find out these things. Now, where are we proceeding from here? You see, if we go back to the previous page, our ultimate aim is to convert this biharmonic equation, the left hand side of this biharmonic equation, written in terms of the derivatives with respect to x and y, in terms of the derivatives with respect to r and theta. So if we have So you see we need fourth order derivatives here. Okay, so here fourth order derivative where this x is involved, here the mixed derivatives are involved, and here only y is involved. So these are fourth order derivatives, but in order to arrive at the fourth order derivative, we have to first start with the first order derivative. So that is exactly what we have managed to do here in the next page. So just like f is a function of r and theta, so also if you have the Airy stress function as as a function of r and theta, so you can find out del phi del x, then proceeding by repeated use of these kinds of chain rules, you can obtain del square phi del x square, del cube phi del x cube, del 4 phi del x4, written in terms of the corresponding r and theta derivatives. Now, of course, one may immediately start thinking that this is going to be a terribly laborious process, and it is so. Okay, it is an extremely laborious, time consuming process. So we are not going to do it by hand. Rather, we are going to fall back on outsourcing our labor to the Symbolic Python used in Jupyter Notebook. Okay, so very quickly, so what we'll do is we'll quickly write down these expressions for del r del x, del r del y, del theta del x, del theta del y, and using just those things we can very quickly build up the derivatives, the various order derivatives, so that we can obtain the expression for the Laplacian and finally the biharmonic in the polar coordinate system. So let's try to do that. So we are now in our browser here. I have already fired up Jupyter Notebook, and we are in our desired folder. I'm not going through the preliminary steps which I have already demonstrated in the introductory videos. So we'll quickly open a new Python 3 based Jupyter Notebook. So this is our new file where we'll do all our work. Okay, and as before, our first job is to import SymPy as sim. That will take a little while. Okay, it's done. Now the first thing we do is we set up our variables, the all important variables r and theta. Okay. All right. Now you please note that that some of the things are quite are very conveniently designed in symbolic Python. So suppose you want to display the theta variable, which is actually written in terms of this theta. So that's the name of the theta variable. But if we run this thing, you see the actual visual representation of it is actually in the symbol that you would write in a piece of paper. Okay, so that's very nice. All right. Now, as I mentioned, our first job would be to write down the expressions of del r del x, del r del y, all these things that we had written down in our writing app here. Okay, so going back to the first page, so we'll write down this as del r del x. So del r del x, let's check again, this is cos theta. So that's done. Next, del r del y. We look at the expression again, del r del y is sine theta. So we use this sim dot sine theta. Next is del theta del x. We take a look again, del theta del x, here we have this as minus of sine theta by r, minus and finally for del theta del y we have, let's check this, del theta del y is cos theta by r. All right, so we have set up our expressions. Now next thing that we need to do is define these derivative operators. So what I mean is, if we go to the next page on this writing app, we have set up this del f del x. So these are like, you can think of this left hand side as the del x operator operating on f, and correspondingly the expansion in terms of the r and theta derivatives are like this. So that's what we are going to do. We are going to set these things up like operator definitions in symbolic Python. So this is del f del r del x plus del f del theta del x. Okay, so what we really want is to use these two expressions, del r del x and del theta del x, and we have to write down the operators where we need to write down the differentiation with respect to r and the differentiation with respect to theta. Okay, so we can quickly do that here. So we define a function which is like an operator function here. We call this as, it is completely our choice, but in order for quick recognition, we'll just give this kind of name, del x of f. Okay, please note that I do not need to first define a symbol or a function f here for this definition, because I'm defining a function. I mean, this is very well acceptable. So del x of f is, so I have to return this thing. So given a certain f, how do I return it? So what I do is, this is I check the expression again. So I need the del r del x in this first term. I write that del r del x, which is already defined in this previous input cell, multiplied with the del f del r. So you see here we have the del f del r. So that is basically just sim dot diff f r, which means differentiate f with respect to r. That's all there is to it. In a similar fashion, for the second term, we use this del theta del x multiplied by the derivative of f with respect to theta, and that's it. Next, in the same input cell, we can set up our second operator definition, which is del y of f, and for this we'll have del r del y times sim dot diff f comma r plus del theta del y times sim dot diff f comma theta. We check once again. This is perfectly all right here. As you can see, del f del r times del r del y plus del f del theta times del theta del y. Okay, so this is done. All right, so our operator definitions are done. Now you see, this is where the real power of the computer algebra system, specifically symbolic Python, is going to be used. If we were writing on a piece of paper, after this step we would have to manually find out the second order derivatives, that is del square f del x square. But we no longer have to do that, because once we have already defined our del x operator, all that you have to do to find out the second order derivative is to make the operator operate on itself. So we can, just like we had defined this del x operator, we can define the second order derivative like this. We can call this del 2 del x2. Okay, this is completely my choice. Okay, this is certainly not part of the syntax of Python. This is my choice what I'm calling this operator, but I like this name. So here what I have to do is I have to use this operator on itself. So this is basically del x operating on del x of f. Okay. Next, for the del square f del y square, I similarly define this thing absolutely same way. using the del y operator that I had defined in the previous cell. Done. Now the moment I have this, I can quickly go and quickly write down my Laplacian operator, which is nothing but the del square f del x square plus del square f del y square. Okay, so since I have already defined these second order derivatives, I can write down this polar Laplacian. Okay, so let's call this polar Laplacian. So again, I'm defining it like a function. Okay, and all that I have to do is just use what I have already done in the previous cell. So del 2 del x to f plus del 2 del y to f. That's it. Okay, see, it's so easy. I'm building up step by step. So first I defined the first order derivatives, then I defined the second order derivatives, and using those definitions I can quickly write down the definition of the polar Laplacian. Okay, so once we do this, let's actually see how this is looking. Okay, so till now we have only defined these things without really looking at the expressions. Okay, so let's set up one function. Let's call this phi itself. Okay, and let's set it up as a function of Rn theta. Okay, so that's we have defined. That's where we have defined the function. Let's just look at it. Okay, let's just type in the name and to see. This is actually displaying phi, but because phi has been defined not as a symbol but as a function, where this capital F is something internal to Symbolic Python. Capital F function is something internal to Symbolic Python. You see that this functional dependence on Rn theta is clearly displayed in this output cell. Okay, so we are good. We can proceed to find out the polar Laplacian of this. Okay, so here when I'm writing polar Laplacian, I am depending on this input cell where I have already defined it myself. So this polar Laplacian here that I'm writing, it is not something internal to Symbolic Python. Rather, it is something which I, the user, have defined. Okay. So here, instead of this generic f, which was only used for the purpose of the definition of the function, I am actually using this operator polar Laplacian on the function that I have just now set up, this phi function. Okay, and let us take a look if it even works. So it takes a little while and it gives me this huge expression. Okay, now if you look at these expressions a little bit carefully, you will see that had you been doing this by hand, you would not have gotten this kind of a huge expression. It would have been a little bit more simplified than this, because there are certain terms which have not been cancelled. There are terms like sine square theta plus cos square theta, which, because in the way that it has been written in an unexpanded fashion or a non-simplified fashion, Symbolic Python by default has not been able to set equal to 1, like terms like sine square theta plus cos square theta, which even in your sleep you can write as 1. Symbolic Python has not been able to do it, but we can help it a little bit in its job by going back to our definition of or what we can do is, before even going back to the definition, we can just see if we can really help Symbolic Python a little bit by asking it to additionally simplify this thing. So we just pass the extra command like this, simplify. Look at this, how beautifully it has simplified. Okay, and if you had done this by hand, you would not have been able to simplify this any further. So this is the most simplified form of the polar Laplacian. Now this we have done by additionally topping up the polar Laplacian operator operating on phi with this extra simplification or simplify command. Because we have done this, why not more wisely go back to the definition of the polar Laplacian itself and embed the simplify command within that, so that every time we invoke the polar Laplacian operator, we don't have to additionally write this simplify. Okay, so whenever possible, you try to simplify the expressions as far as possible. This is not only for the purpose of aesthetics, okay, not just to make it look beautiful, rather for subsequent calculations where you have to utilize this polar Laplacian definition as part of your 2D elasticity solutions, it'll really help Symbolic Python to do the further calculations. Okay, so with that motivation, we are embedding the simplify command in the definition of the polar Laplacian. And now if we come back to this cell and delete this simplify command from here, let us see if it gives us the same result. Okay, so previously it was giving that really long expression of over 4 or 5 lines. Now we have embedded the simplify command in the definition itself. Let's see if this thing works. Okay, so it works very much. Okay, even without the simplify command here, it works. So that's very good. Now the moment we realize that this is very good and it's working, what we can do is we can immediately go and find out the polar biharmonic. Okay, because the polar biharmonic or the biharmonic itself, the polar is just a just a description to explicitly mention that we are working in the polar coordinate system, but this is the Laplacian. Okay, so for the biharmonic, all that we have to do is to make the polar Laplacian operate on itself, because del 4 you realize is nothing but del square operating on del square. Okay, so let's define this polar biharmonic just like we had defined the polar Laplacian, using this generic function f, and we return. Okay, we don't use any del 4, del x4, anything like that. We just use the polar Laplacian operating on itself. Polar Laplacian of the polar Laplacian of f. That's it. Now let's test this out. Let's see what the polar biharmonic of my phi function, which I have set up, what it looks like. Now see, if you were to check these terms manually, you will realize that there is no way to simplify this further. Okay, I repeat, there is no way to simplify this further. And you realize that if you had to go from this polar Laplacian to this polar biharmonic manually on hand, on a piece of writing on a piece of paper, how much labor you would have to undergo. All of that is bypassed by outsourcing the algebra to this Symbolic Python. So it's a big help. All right. So let us proceed now and find out the expressions of the stresses, because I mean when you are doing a 2D elasticity problem, your one of the primary interests would be not to stop at the solution of the biharmonic equation. Rather, once you get the biharmonic or the eddy stress function in your hand, your interest, one of the primary interests, would be to obtain the stress fields, and later on of course to obtain the strain fields, the displacement fields, like that. Okay, so we know that sigma xx is del square phi del y square. We can write that down even. So let's quickly remind ourselves that we already know that sigma xx is equal to del square phi del y square. Sigma yy is equal to del square phi del x square, and sigma xy is equal to minus of del square phi del x del y. Please note that all of these things are written in the rectangular Cartesian coordinate system, but here what we are trying to do is obtain the corresponding forms in the polar coordinate system. And since we have already defined the del 2 del x2, the del 2 del y2, all these things we have already done, so we can we believe that it should be possible to obtain the corresponding expressions of this sigma xx, sigma yy, and sigma xy. But does that mean that our job is done? suppose you were to convert this del square phi, whatever this expression is, del square phi del y square, in terms of the derivatives involving the r and theta. Does that mean that our job or our objective of finding the stress fields in the polar coordinate system is done? Certainly not, because in the polar coordinate system you note that sigma xx, sigma yy and sigma xy is meaningless. What you really need in the polar coordinate system is sigma rr, sigma theta theta and sigma r theta. What are these? Well, uh, to understand this, all that you have to note is that if you're really looking at this xy coordinate system like this, so this is our x and this is our y, you can think of the I mean, you don't have to think of it like it. I mean, it is what the r theta coordinate system is simply like this. Okay, where this angle is theta, this is the r coordinate system, this is the theta one. Okay, you can think of it like unit vectors er hat and e theta hat, all those things. But uh, so this is a coordinate system which is rotated from the xy coordinate system by theta. And the moment you realize this sort of a transformation or this sort of a relation, geometric relation between the orientations of the r theta coordinate system and the xy coordinate system, you can go back to the mathematical preliminaries chapter and use the rotation tensor or the rotation matrix to obtain these things, the sigma rr, sigma theta theta, sigma r theta, from the sigma xx, sigma yy and sigma xy. Why? Because you understand what we are basically asking is this, that in the xy coordinate system we have the stresses in this fashion, sigma xx, so this is the matrix representation of the stress tensor, sigma xx, sigma xy and sigma xy, sigma yy. From this, what we want is again the stress tensor, but in the r theta coordinate system, where we have sigma rr, sigma r theta, sigma r theta, sigma theta theta. Okay, so in order to go from here to here, all that you have to do is to use the rotation matrices appropriately. Okay, so we have already done that as part of our problem sheets, these kinds of second order tensor transformations in our mathematical preliminaries chapter, and we'll directly utilize those things here. Okay, so let's get back to the Jupyter Notebook. So first of all, our first job is to convert the sigma xx, sigma yy and the sigma xy, those things in terms of the derivatives of r and theta. And further along, we'll transform the stress matrix itself in from the sigma xx, sigma xy and sigma yy to the sigma rr, sigma theta theta, sigma r theta. All right, so we have quite a few jobs in our hand. Let's address them one by one. So again, we define this kind of sigma xx. All right, now this is defined just directly by using the del 2. So del 2 del y2. Okay, so let's not forget that the sigma xx del 2 del y2 of phi. Okay, for our generic definition, this is just f. All right, similarly, sigma yy f is this. And finally, the sigma xy definition is this. Del del x of del del y of f. You could equivalently write this as del del y of del del x of f. It's the same thing. Okay, you can check this yourself. All right, so our definitions are done. So we can quickly check this. Okay, so sigma xx of phi. Okay, suppose phi is the generic eddy stress function. We don't know its form right now, but let's say this is just a function of, we have set it up as a function of r and theta. So what is the form of this sigma xx? So look at this, the huge expression. Okay, and we'll see whether we can simplify this or not later. Okay, right now we don't need to display this thing, so we'll cut it out. Rather, what we'll do is let's just delete this cell. Escape D. Okay, so that cell is deleted. What we'll do is we'll set up our stress matrix using this sigma xx, sigma yy, and sigma xy. So let's set this up. Because we are working in the rectangular Cartesian coordinate system, I'll call this sigma rect of f, and what this will return is the matrix form. Okay, the matrix form involving the sigma xx of f, sigma xy of f in the first row, and sigma xy of f, sigma yy of f in the second row. That's our definition. Okay, I am not going to display this because it's going to be a huge thing. All that I have to do now, that I have obtained this matrix in the stress matrix in the rectangular Cartesian coordinate system, I have to utilize the rotation tensor to transform this to the r theta coordinate system, so that from that polar coordinate stress tensor, I can extract my desired sigma rr, sigma theta theta, and sigma r theta. Okay, so let me quickly go to the writing app and remind ourselves that the expression that we're looking for is basically for the stress transformation. Okay, for the stress tensor transformation from the rectangular Cartesian coordinate system to the polar coordinate system. What we use is sigma, so this will be polar, this will be equal to, this is my rotation matrix multiplied by sigma, where this sigma is written in the rectangular Cartesian coordinate system, multiplied by q transpose. So q sigma rectangular times q transpose. So when we do this thing, we'll end up with this stress tensor in the polar coordinate system. So what is this q? We have cos theta sin theta minus sin theta cos theta. So you can actually check this by quickly going back to the diagram that I had drawn earlier, and considering the angles that this r is making with the x and y. So the q11 term, that is the first row first column term, that is the cos of theta, and the q12 term is the cos of 90 degree minus theta, which is a sin theta. And similarly for the second row, we have this angle and this angle to take care of, this entire angle that theta makes with this x-axis, 90 degree plus theta, and this theta angle that this theta makes with this theta axis makes with the y-axis. So that's how we obtain the minus sin theta and cos theta. So we can go back to Jupyter Notebook and implement this definition. So q is equal to we need two rows here. So cos theta, sin theta, minus sin theta, cos theta. You will notice that there is a jump in the input cell numbers here from 18 to 42. That's because I've made some typing mistakes in between, and I had to edit that out. All right. So using this Q matrix, we can now define the sigma polar. The sigma polar is equal to, we'll set it up like a definition as before. Sigma polar of f, we return it. So this is the expression which we had written up in our writing app: q times sigma rectangular of f times q dot t. So this q dot t is basically telling Symbolic Python to do the transpose. Okay. Now let's extract the sigma rr, the sigma theta theta, and the sigma r theta components out of this sigma polar matrix. So for that, I'll again set it up like function definitions. So this will be sigma polar. I want the element, the setting in the first row and the first column of sigma polar, and because Python's indexing starts from 0, we have to use this 0, 0 for the first row and the first column. Okay. Next, for sigma theta theta, please note that I am just writing this in a short form as tt for theta theta. This will be returned sigma polar 1, 1, basically the second row and the second column. And for sigma r theta, sigma polar 0, 1. Okay, let's see what the sigma rr looks like. So I want to input within it the phi, so sorry, I've made a mistake here. So this is f, because the sigma polar in the previous line has been set up as a function definition. Okay, so we have this huge expression coming out for sigma rr. Okay, very huge expression. So probably if we ask Symbolic Python to simplify this, we'll get a shorter expression. And as you can expect, we have indeed come up with this shorter expression. But please note that suppose you were writing this on a piece of paper, you would not have stopped at this. Rather, you would have written this as 1 by r del del r of phi plus 1 by r square del square phi del theta square. So if we expand this out, if we give the further command to expand it, it will make it look much more. It will present in a much more familiar form. Okay, not perfectly the way that you would write on a piece of paper, but much closer to it. Okay, so since we are writing all these things here, it will be better if we just embed these commands in the function definition for sigma rr itself. Okay. All right, now let's see. So it immediately gives us this nice simplified looking expression. Next, let's check for the expression for sigma theta theta. And again, you see it's such a huge expression, but probably if we simplify this, it will give us a much shorter expression. Let's do that. And as you can see, it's good. And because there's just one term here, we don't even have to expand it out. So we can just copy this simplify command here from here and put it and embed it in the function definition for sigma theta theta itself. Okay, done. And now if you come back here and re-implement it, it should give us the nice simplified expression directly, which it does. Next, let's check for sigma r theta. So again, this huge expression. So probably we need to simplify it. Let's check that and see. Nicely it is giving us this thing, and maybe it's not a bad idea to expand it out also. So let's do that. Now as you must have noticed that when I defined the sigma r theta, I used the element in the first row and the second column. However, we expect that the sigma polar matrix, just like the sigma rectangular matrix, would be symmetric. So the theta r coordinate, that is the element sitting in the second row, first column, should be the same. So let's check that. So suppose we define sigma tr of f, and we return the first row, the second row, first column, and let us not forget to issue the simplify and the expand, so that later on we don't have to do it. And the previous one also expand. Okay. So ideally, our expectation is that sigma rt should be equal to sigma tr. That's what we want to check. Okay. So we go back to this line, delete the simplify and expand commands because we have already embedded them in the definition, and just check out the sigma tr. So we check this carefully, they're perfectly the same things. Okay, so at least the symmetry is very much satisfied. Now with these definitions in hand, we are in a position to go on to the solution of problems involving the polar coordinate system. Okay, now you may expect that these definitions that we have written down within this particular file, this will have to be utilized over and over again in various files. Okay, so whenever we set up a new file for the solution of a new problem in the polar coordinate system, these basic definitions where we have set up our polar Laplacian, the polar biharmonic, and the various stress definitions, these will have to be set up again and again. Okay, and that can be quite a tedious job. Like in every new file, if you have to do that, it's not very convenient. So what we can do is we can collect all these definitions which we have set up here, and we can put them nicely in a separate file, and we can invoke those definitions as and when we need in the separate in every new file that we use. So let me demonstrate that last bit of actual use very quickly. So what we'll do is we will set up a new file. Okay, so let's go back to this navigation tab, and you see back when we started our new Jupyter Notebook file, we had clicked on this Python 3. Now instead we can just click on this text file where we can put in the so this text file will be initiated as a text file, but we can convert this to a Python file. Okay, that's what we'll do. Okay, so this is our Python file. Let me close this unnecessary tab. So first of all, you see that I had started by this thing. So I'll just quickly copy paste the various things in this new file. What I can do is I can save this file. If rename this actually, let me rename this as polar utilities .py. So this .py extension makes the system understand that it is a Python file, not a Jupyter Notebook or an IPython notebook file. Rather, it's a simple Python file. Okay. sorry, there's a clash of the folders because I'm currently in a different folder. So let me go back to our for lectures folder, and here I will set it up. Let me go back to the 2020. Okay, so let me close this one. Let's set up a new file here. Okay, so I rename this as uh, polarutilities.py and continue copying the various uh, lines into this. As simple as that. I just copy this here. And you'll see in a moment the great convenience this will afford us uh, as we open new files later on. So everything that we had defined, we are going to copy. Please note that I don't need to copy this pi function, okay, because all my definitions are in terms of this generic f function, so let it be like that. I also don't need to display these or to copy these lines which were just for the purpose of displaying. Copy the polar biharmonic. All the actually utilizable lines that I copy, all the function definitions and everything. You see we have defined quite a bunch of functions and this will be utilized again and again. I'm almost done here. So you see I've skipped all those lines where I just utilized the function definitions to display the various things. Those I have not copied. Okay, only the things that I needed, those I have copied. Okay, so just save it. Now let's say we close this file. Okay, I have saved it. I'll just close this file. Okay, what I will do now, you see back in my navigation tab, this was the untitled file that I was working on. Okay, it is still running. What I can do is I can just shut it down. Okay, it does not mean that it is deleted, it's just it's gone inactive now. Now what I will do is I will open up a fresh file. Okay, I'll just open up a fresh file, a fresh Jupyter Notebook file. So you see back in my navigation tab, this has gone to the green color, this untitled one. This untitled one is this new file that I have opened. Okay, so let's rename this. Okay, just rename this instead of untitled one, something meaningful. Maybe let's call this polar polar demo 2. Okay, I'll go back and name this untitled file as polar demo 1. Okay, so let me get back to Polar Demo 2. So you see I have not imported SymPy or anything here. However, what I will do is I am going to import this Polar utilities. Okay, and the way that I'm going to import it is just like a just like the import of like the general way that the packages are imported. So from Polar utilities I'm going to import everything. Now earlier when we were importing Symbolic Python, we had imported as import SymPy as sim. We might as well have imported that as from SymPy import star. This import star basically means that I am importing everything that is within that package Symbolic Python, okay, into the current file. So that's exactly what I want to do here. Now this kind of a command from any generic package, import everything, this is not exactly encouraged in the Python community nowadays. Okay, so despite that I'm doing it here. That's because this is a very small package where something and this is completely under my control. I know what I have defined here, there is no problem. And the good thing is within it I have imported the SymPy as it should be, as it is actually encouraged in the Python community. Okay, so the main reason that it is suggested that we import it like this is that if within the SymPy package there is something, there is some function or some variable which probably clashes with another package, and there is a lot of clash with the NumPy package, the numerical Python package. So there won't be any clash if we just prepend the function names like this sim dot cos theta or something like that. Okay, otherwise there may be a clash, or at least some sort of confusion will arise. But at least for our current case there is no confusion like that. So we are safe to do it, and we just do this kind of a import. You see it imported without any error. Now the good thing is, even though currently in this Polar Demo 2 file I have not imported Symbolic Python, rather I have imported the Polar utilities. Let's see, this Polar utilities file within which the import of Symbolic Python has been done, and whatever else has been defined here that is currently available here. Okay, and I can check that out. So suppose I so see here I have also not defined the arc theta, but suppose I write theta. Okay, like if you were to open a new file and just write theta, it's going to give you an undefined error or something like that. Okay, but now you see it understands, because at the background all this importing has already been done from this Polar utilities Python, which we have in which we have written all the utilizable things. So what we can do is we can set up this generic function phi which is dependent on r and theta. And now let's say we want to display this sigma rr. Okay, see in this entire file nothing, like just 2 lines have been written here. Okay, and these are just, I mean, it has nothing to do with the sigma rr, but based on what we have imported in this first line I'll be able to directly use it. So if I write sigma rr phi, it should actually give me the answer. You see, similarly for sigma tt. So you see the great convenience this affords us. This Polar utilities file, as long as it is there in the current folder, you should be able to import it like in this first line here, and then continue with your actual solution of the problem. So with this I end this part of the rather long lecture, and we'll continue with the actual solutions of problems in polar coordinate system from the next one. All right, thank you very much.